Hello, how are you today? How's everything going? We're getting down to the end of the course. Um, we are now to using collections, and this is actually the best way to work with memory and data is to use the languages support and also to work with that standardized memory is going to be important for the stability of your program. It really is. If it's standardized and it's implemented already, use it. And so the collections that we're going to be talking about today are standard collections to be used in lieu of creating your own linked list. You don't need to create your own linked list. Uh, and then also like dictionaries and cool stuff like that because I use dictionaries a lot for solving problems. And C++ has dictionaries, Java has dictionaries, and we call them a map. That's what we call them, a map. So let's get into the PowerPoint. We're not going to get too nitty gritty into code. Let's just do. I want to do an overview of things because we've already talked about dynamic data structures and how things get dynamically linked with a linked list. Then we throw queues and stacks at you. Guess what? Queues and stacks is just a linked list. But you use the linked list in a certain manner for queues and stacks. And that's it for queues and stacks. They're linked lists. Queues and stacks can be implemented with arrays. You don't have to use a linked list to implement a queue or a stack. It's just the manner that you send and retrieve the data that determines whether it's a queue or a stack. Uh, and so you can have what's called a priority queue where you put into the dynamic data structure based on a specific value, and then it'll work. You can add those to what a queue is that first in first out behavior. So think about a grocery store line. If you're going to create a linked list or an array where the data needs to go to and from the memory, your RAM, in the manner of like a customer's going through a grocery store. And if you were able, or a grocery store line, I would not want to be. I want to be if I'm the first customer into that line, I want to be the first customer out of that line. That's the way that works. And so there's a lot of ways of solving problems using the mechanics of a queue and a stack, even though they're implemented in either an array or a linked list. It's just about where does it go, how does it come, and when. Um, and then we're going to skip over to maps a little bit, but let's nail through here some of this. Uh, Queues and stacks, maps are your dictionaries, and that's what we're going to be talking about. And all these abilities, these data structures, are the way to go when it comes to having complex memory management. And one nice thing about Java is you can work with these things and you never have to worry about a memory leak or deleting the memory once you've asked for it. That's the way this sort of language works. So we call it a garbage collector. And so with these, I call them super languages: Java, C Sharp, uh, in some ways JavaScript. Because JavaScript has a garbage collector. And basically what it is when a variable goes out of scope, there's a loop that's always running in the background, and looking at the stack. When a variable goes out of scope, it will automatically delete or free up that memory. And you don't actually delete the memory. You just tell the operating system, I'm no longer using this memory. You can have it back. So yeah, use the collections. They're proof. They're already error proof and optimized. And of course, you can implement them in different ways, uh, such as with an array list can be implemented as a queue. or a stack. Linked lists can be implemented as a queue and a stack. And what I'm talking about when I say implemented is I'm talking about how it's used. So a lot of the interfaces that you have are abstract, and you will need. Now here's the thing with these collections. They're templated. And here's the reason why they're templated. And I think it's kind of funny. It's hilarious. Because the previous videos I was talking about how this language does not need to be templated, because you can box and unbox the variables down. You can cast it down to where it's an object and store objects, and then look up the stack for whatever you need of that object for dynamic binding. But it turns out that the people who love templates screamed so much that they implemented them. And here's why they implemented them: because they're faster. They're more efficient. They're more efficient and faster. And speed always wins in computer science, guys. Speed is dollar signs. Speed is dollar signs. If you're able to come up with a better streaming for video, and you patent that streaming algorithm, and everybody wants your streaming algorithm because it makes their streaming so much better, more clear, faster, whatever. Money in the bank. That's all it is. So speed is always an issue. And that's one thing about these, when we work with these abstract data types and dynamic representations for queues, stacks, and linked lists, hey. But let's go back to the reasons why dynamic structures are important. Is because with an array, you can't just ask for one more. You can't just say, hey, I want one more. I need to add one more, but my array does not have the size for it. Now, what does that mean? What does that mean? Well, if you have an array, and yeah, Mr. B is on his crazy scribble time. Yeah, that's a little nutty, isn't it? Yep. Okay, this is an array. An array list. And you got items. And typically the way that an array list keeps its efficiency is if you try to add one more item than it has, it asks for the operating system. It says, give me more memory. And the operating system sends back a pointer with that more memory. And then it has to copy each one from the old list into the new list so that you can add your new value. And so that's the weakness of array lists. And that's implemented in many different languages. They call them different things. In Python, they call them a list. I mean, it's an array. And it's what we call contiguous memory blocks. And what that means is each of these guys are going to be in order. And that's why arrays are so efficient, is because when you have your array, let's say that this is an item on your array, it's at address 3000, and each item in the array is 20 bytes. So your next one would be 3020. And then your next one would be 3040. And that's how the operating system gets to it, or not your program, because your program only has to have that initial reference till it has all of them. So it has all of them with that first starting reference, address 3000, and then it'll know that there's 3 items there, so it'll know the next one is at 3020 based on the size of the item that you're storing there. And it could be an object, a customer object, whatever. It's going to be a fixed set of bytes. So linked lists, again, why? Because what if we just want one more? One more. That is so inefficient to do with arrays. So the linked list solves that problem. But here's the problem with linked lists: you got to start at the beginning and traverse through each guy, and that causes a problem. So guess what? Google invented binary. Well, no, they didn't. They implemented binary trees with Python in a very unique way, and took over the world. Well, okay, they took over most of the part of the world, but binary trees is an implementation of two linked lists, left and right. And so a binary tree, you are storing a left and right linked list for every node. And that gives us the ability. So instead of one next, we have a left and a right. And so what ends up happening is we kind of look at it like this, and it's just a linked list, but each link has a left and a right, so each one can branch out. And we would put values in here dependent on where values were at. So we would go and we would store the data in this tree in a manner where it's easy to get back that information. We just go to the front of the tree and we just need to look here. Oh, there it is. Instead of 1, 2, 3, 4, 5, 6 steps, we're now to 1, 2 steps to get our data. And the bigger the binary tree, the bigger the data set, the more efficient it is. It's crazy. So that's how binary trees, and they just work by having a left and a right side, a node, just like a linked list, just like what we talked about. Of course, we're only having an introduction to linked lists by, we built our own. Yeah, great. So that gives you an idea of what dynamic data structures look like. Self-referential dynamic data structures. Okay. So we've already talked about this. We've covered this and the next and stuff like that. So we're good here. Let's not even talk about most of this. Other than, I think, yeah, we've already covered this. This is all from last week's stuff. Now we get into queues, and you can implement a queue as a linked list, but here's the idea is that what the heck is going on here? Where's my whiteboard? Ah, you silly thing. My whiteboard's messing up. Yeah, I know. You really want more scribbles, don't you? Yeah, you're asking for it. I know. Oh, jeez. I'm being weird. Okay. Enough of that. All right. Let's get into queues. Okay, let's say that this is an array, and it could be a linked list too. Doesn't matter. Because the linked list you can insert between nodes, you can insert at the end, you can insert at the front. So a queue is just where you put data. Let's say that you always put data in a manner where you can access it so that it accesses first in, first out. So you will have some kind of abstract insert function where it will insert it into the data in a manner so that when you say pop or get, that it's first in, first out. So for instance, if this is an array, we insert front. Here's our front item, front item, front item. We keep inserting front, keep inserting front, keep inserting front. And then we know that when we retrieve, we get the data because we are inserting front. We know that we need to get front. And then this pops off. Then we get another front. That pops off. We get another front. That pops off. That's all first in, first out. First in, insert front, insert front, insert front, insert front, insert front. And if you were doing this as an array, you would have to shift some of these nodes around. Actually, no, you wouldn't, because you would do an insert rear and a remove rear. You could do it. No, insert rear, remove front, or whatever. So a queue is just how you get the data. That's all. It can be implemented as an array or a linked list. It can be implemented as a binary tree. In fact, that's the reason for binary trees, is to get data in order fast. All right, so a linked list, same principle applies. Insert front, insert front, insert front. Then your pop, it will be remove front, remove front, remove front, so that you are grabbing data first in, first out. Now a stack you can visualize as a stack of plates at Granny's buffet. Every time you put on data, you're using you can think of it as an array as well, but okay, Granny's buffet is going away. Okay, whatever. All right, here's our stack. We start with we put a plate on of data, then we put another plate of data on another plate of data, another plate of data, and when you remove it, you remove from the top. So what it is it's insert what was first in is last out. So you will stack it up and then remove it from the top down. And you can think of it again with the array idea, is that if we were going to do first in, first out, or no, first in, last out, that means that we add an item here, we add an item here, let's say we do insert front, we add an item here, we add an item here, then instead of removing from the front, we remove from the rear, because it's first in, last out. Then we remove this one. Then we remove this one. Get the data, pop it, whatever. And then that's the last one. So it's first in, last out. And there's actually algorithms that are useful if you use these two memory structures. There are algorithms that solve real world problems. Well, duh, grocery store line. But the stack and the queue can be implemented in unique ways to solve problems with elegance. Same kind of thing with recursion, but hey, if you're gonna use actually, don't use recursion. Just don't. Recursive referencing is okay. Like linked lists, whatever. Yeah. All right, let's go in. We talked a little bit about queues, and the next thing I wanted to get to was a little bit on maps. Trees. Actually, you know what? Let's talk about trees. That's good. Okay. So more on Mr. Scribbly. All right. Let's say that we have an item, or we have items, and I'm going to use simple data types for this because it's really easy, but these would be more complex. 1, 3, 10, 4, 1. Oh no, 2. Okay, so it's going to be for when I'm just getting data one piece at a time. It's like the linked list. When I want data one piece at a time, to add it one at a time based on a stream of data where I don't know where it ends, it's going to take this stream and kind of imagine that this number is coming to it, and then after some time this number comes to it, and after some time this number comes to it. So it's all responsive based on the data you initially send it to. You send to it. So we're going to create a binary tree. And what a binary tree is it's a node that has a left and a right. Instead of next, it has left and right. So it has self-referential abilities because linked lists, we just have next. But with a binary tree, we've got a left and a right. Well, why do we have a left and a right for a binary tree? Well, because we use it so that when we insert data, it inserts it in a manner where it's already sorted. Frickin' amazing. It changed everything. Everything changed because of the implementation of binary trees for search engines, Google. And I've used this metaphor a lot. Not metaphor, simile, whatever. back in the 56K baud days, I would sit down to Alta Vista. It was called Alta Vista. And I would search. I'd go up and get my coffee, wait around for a few minutes, and then the search results would come up. I'd get coffee, drink some coffee, sit down, and then the search results would come up. Google came onto the scene with their search engine. And Alta Vista became Hasta La Vista. Goodbye, Alta Vista. Because Google, when I put in a search term, bam, immediate results. And not only that, but better results. It's crazy. So here's how it works. When you're inserting items, and this can pretend that this is a Google website crawler, and they're inserting topics or keywords in order from your web page. So we are first going to insert and create a node based on the first data piece we have. It's 1. Then when we insert another one, we follow rules that we start by comparing 3 to 1. Because 3, we want to insert the value 3 into the binary tree. But we got to start by saying, hey, where does it go? Does it go to the left or the right? Because it's like linked list, it's just next. That's easy. Next, next, next. But what we do is we say, hey, if it's less than what value is here, we're going to put it on the left. If it's greater than the value that it visits, we're going to put it on the right. So it looks, and we say, hey, 3, you're greater than 1, so we're going to find a home for you down here. And that's where 3 lives. Okay, then 10 comes in. We look at 10. Oh, it's greater than 1. 10, it's greater than 3. So 3 goes on to the right branch of this node. Or 10 goes on to the right branch of that node. And this has a branch, left and right. Then we get a 4. Well, it's greater than 1. It's greater than 3, so it goes to the right. It's less than 10, so it goes to the left. You see what we're doing here? 4, we start by comparing it. Here, it's greater than that. Then we go there because we're trying to find a home for it in the linked list. Because we're sorting it as it's being inserted. Because you can traverse a linked list in order really quick and get to data that you're looking for extremely fast. So we look at the 4 and say, oh, it's greater than 3. Then we go over here. Oh, 4 is less than 10. We put it here. And it has a left and a right that point nowhere as well. Then we get to the 2. 2 is greater than 1 and less than 3. It goes here. And then for this example, we have a problem. Because the more balanced the tree is, the more branches, the more it looks like a tree and comes down like a cone, the more efficient it is. So then what we have to do is we have to modify our data to go into the tree so that the tree is created balanced. And that will speed up search results even faster. So then I should put the data in because you see right here, initially, everything went to the right. So we should have 0 here so that we got one that goes to the left. Then let's do a negative 1. Negative 1 is less than 0. It goes over here. Negative 1. Let's do a let's see, what's greater than, negative 1 is less than 0. Let's do a, whatever, you know, it's getting, I'm just like trying to show you a balanced tree here. I'm not choosing very good numbers. And I'm trying to show you the balanced tree with these numbers, and it's not clicking yet. Let's just try negative 2 and see where, no, let's go negative 10 and see where it takes us. Okay, negative 10 is less than 1, yes. Negative 10 is less than 0, yes. Negative 10 is less than negative 1. Well, what's greater than negative 1? What about negative 1.5? Negative 1.5 is less than 0. Negative 1.5, oh my goodness, is it less than or greater than? It's less than. Negative 5, is it less than or greater than negative 10? Well, negative 5 is greater than negative 10. Yeah, it gets kind of squirrely, doesn't it? Yeah. Let's try negative 0.5. Negative 0.5 is less than 1. Boom. Over here, negative 0.5 is greater or less than 0. Boom. Negative 0.5 is greater than negative 1. And so that would go over here. Okay, so this is my attempt at a balanced tree. And remember, each of those nodes and data that's in that node has a left and a right, just like a linked list has a next. So it's really like a souped up linked list. Yeah. And here's the value of it is if we're looking for 0.5, we just go 1, 2, 3, 4 steps and we get to 0.5. And so it's a lot better than if you were going through a million items in a linked list and 0.5 was at the end of the list, because you would have to start at the beginning to find 0.5 and go all the way to the end before, oh, it's the very last one, damn it. And then you would find it. And so that's where binary tree really comes in. Now, another thing that we talk about is where we talk about a map. Now, a map is what we call a hash table. A hash table is another memory structure that came on as part of more of the, it was part of the journey to binary trees. A hash table was created to solve issues of finding data in an array faster. And what it involves is that if we wanted to store 3, where it would go would be based on a function of the value that we want to store. And let's say that we store every value based on its value itself minus 1. So then this is the algorithm for our hash table. We take the value, subtract 1, and that's where it goes. So 3 would go right here. 0, 1, no, 3 would go, okay, let's say minus 2. 0, 1, so 3 would go here. Oh my God, this is horrible. All right, this is horrible. All right, what is a hash table? What is a map? A map is where you have an array. It's an array. It uses an array because arrays are fast and efficient. And what a hash table does is it stores the data in the array. Oh my God. Based on the value of the data, guys. So we know where it goes in the array because it's stored in the array based on its value. Okay, so let's say that we got our horribly drawn array. And let's say that we have the data AOL to store. And let's say that I create an algorithm that decides where AOL is stored based on the values of these guys. So let's say that A is the value 1, 0 we're going to assign the value 2 to, and 1 we're going to assign the value 3 to. And then we would say 2 plus 1 plus 3, that equals to what? 1 plus 2 plus 3, 5, 6. So then we would decide that AOL 0, 1, 2, 3, 4, 5, 6, AOL goes here. Because we assigned values to the A character, we assigned values to the O character, we assigned values to the L character, counted them up so that we would know that based on the value of what is being stored, where it goes in the array. And here's the thing is when you're working with hash tables, your arrays are gonna be limited in size. So you got to take that in consideration where you store items, because that has to be based on size. And you can use the modulus size we usually use modulus size to some kind of form of that, so that we modulate the number within the size of the array. So we will take the value 6, modulate it by size, and get the remainder, and that's where we would store it. Something like that. But it all comes down to a slick algorithm that looks at the data and decides where that data goes. And you know what we call those when we discuss dictionaries in collections? We call those key value pairs. So what is the key? The key could be anything. The key is what's used to hash to where we put the value. So let's say that we have the key Adam, and the value AOL. And we want to store Adam, or we want to store AOL using the Adam key. And so the algorithm would do some mumbo jumbo, boom, 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 count up whatever, and determine that this key goes to this index, and then AOL will be stored there. And so you are able to retrieve that value within the array that has been dynamically created for you and is managed on the back end, so that you don't have to ask for one more. It will actually double, but it'll give you enough. Eventually it'll have to if it gets big enough, it'll have to double the array and do some memory management. But the propensity for that to happen is a lot less, because you're inserting items in a controlled manner, because this algorithm would take into consideration, when it decided what index, the size of the list, the size of how much RAM that you've put aside for this variable. And that's all managed for you on the back end. And that's great. That's great. Just use it. Just use it. And that's what you're going to do with linked lists and everything else. And yes, there's templates involved, because why? Well, the whole reason for binary trees is efficiency and speed. Why? Because you can take over the world like Google. It's money in the bank. It really is. All right, guys. That takes us, we know what? We talked about binary trees. We talked about maps, dictionaries, and hash tables. You've got the broad strokes. Now you can get into the details and actually start using these collections. And I'm going to refer you back to your book. At this time, I'm not going to have any fun coding adventures just for this module. I might. If you see some down there, then I've added it. But yeah, take care. Bye-bye.